So let's talk about another observational technique that's in the news. You see January 14th, an idea was put forth to build, this is sort of similar to what we were talking about just before the break, having complementary sensors for gravitational waves. So we have gravitational wave sensors. What can we do to get the most out of when we see a gravitational event? And by the way, I have to correct myself. Earlier I said gravity waves. So we should make a distinction between gravity waves and gravitational waves. The way this has evolved in the press and in the science literature is gravity waves describe a phenomenon in Earth's atmosphere that we sometimes see here because we're close to high mountains. Fluctuations in cloud density that occur because of wind going over high altitude areas. Those are called gravity waves. Gravitational waves are the ones that are pertinent when we talk about cosmology. So I don't want to make that mistake again. So the issue is, how do we complement gravitational wave sensors with the right kind of stuff that can, as I said earlier, can quickly look at a spot? What could they expect to see in a detectable signal? And the answer is X-rays. So there's this proposal to have a gravitational wave sensor system, such as we are building, linked to space-based X-ray observatories. And we need to do the X-rays in space because X-rays don't propagate through the atmosphere. And so there's this proposal that's starting to rattle around, and this is the way, by the way, the astronomy community works. Ideas are thrown out into the marketplace of ideas, and some of those ideas survive and get the attention of people who are going to serve on the decadal surveys that I mentioned last time. That is, NASA organizes these expert panels to discuss what should we do over the next 10 years.
Question.
Yes, sir.
You say that X-rays don't get through the atmosphere, but we know gamma rays do. We're talking about these high-frequency
right.
waves.
Well, gamma rays sort of do. That is, we see the effects of gamma rays. Gamma rays that encounter the upper atmosphere produce a shower of debris.
Oh.
That's what we see. So gamma rays.
Well, I thought they affect human beings in terms of
yes,
carcinogenic.
Gamma rays are the highest energy electromagnetic waves, and some of them actually reach the ground. Do you guys know the cow? Did I tell you the cow story? No? Okay. So a friend of mine who lives in Fort Collins is part of a consortium that built an array of gamma ray sensors. They work in a restricted region of energy, which happens to go through the atmosphere. And these gamma rays are unbelievably powerful. They're bombarding the atmosphere right now. We don't know where most of them come from. So anyway, a consortium, international consortium, built an array of sensors to detect gamma rays at the surface of Earth. And this is sort of like trying to find neutrinos. Remember I said that neutrinos are flying through us by the billions all the time. The chance that one will interact in a sensor that we built is very small, but there's so many of them, occasionally you're going to get a signal. So what they do for these gamma rays is they take a big water tank, kind of about the size of the space between the tables, and they put it out in an array of them out in a rural area. Usually they go to a rancher and they say, we would like to put water tanks out on your ranch. And the funding was, for a while, there was funding to do this in both America, North America and South America. And my friend, who's from Argentina, was working with the science team down there, and they had a big array in the Pampas, the flatland of Argentina, and they have water tanks everywhere. Inside the water tank, they have light sensors. So if a gamma ray happens to make it to the ground and interacts with the water, a fraction of these interactions produce a pulse of light that's indicative of that it was a gamma ray event. So he was one of the scientists involved, and they were in, I don't know, some city where they were managing the system, and the director called him and said, we have an issue going on with sensor number 37 or whatever. It's out in the rancher's field, and it seems to be moving. And it's a water tank, as I say, as big as the space between the tables and maybe 6 feet high, and it weighs 10 tons, maybe more. It seems to be moving. So they gave him the keys to the truck and a radio, and they sent him out into the pampas. And he's driving around, and they knew where they put the tank, so he went there first. There's the tank. So then he's trying to figure out, why is the tank moving? So he had the GPS signal. He went to the place where the GPS signal sent him, and there was a cow who had been using the tank, the ladder on the tank, as a scratching thing. The cow was scratching, and there were wires hanging down, hooking to all the technology, and the radio antenna, and the cow had gotten tangled and walked off with all the electronics, including the GPS receiver that told them where the tank was. So, remember last time we were talking about on Keck, there's a big sign, beware of invisible cows. Yeah, so you got cows seem to be in the news. Okay, so the idea here is a proposal to X-ray space telescope linked to LISA, which is the space-based version of LIGO. LIGO being the gravitational wave sensors that are being in use now. There's some benefits to gravitational wave science to having a trio of spacecraft in orbit and do the same thing that LIGO is doing on the ground, do it in space. You'll be able to see different kinds of events, of mergers of massive objects, if you do the measurement of space-time distortion, if you do it in space. And the idea is to complement that with an X-ray observatory. So this is the beginning, and I believe this was, European Space Agency, in the 2030s. They're going to focus on getting X-ray observatories to complement LISA.
Do those X-ray devices in space have to point at the right place?
They do.
Okay.
So we're counting on having enough sensors to triangulate and say, something happened right there, and then the X-ray observatories take a look. Because remember I said, if you have one of these mergers, the signal you're going to get right before the event is over is the very high temperature accretion disk events. That's what you'll see. And that will heat up that accretion disk will heat up the atoms to a point where they're not producing light, they're producing X-rays. All right, so there's some details here if you're interested in that. Oh, this is fun. So this is actually several years old. I had not seen this before. That's what I'm talking about. This is an observation using the big array in New Mexico, the very large array, which is radio telescope out in the desert. Has anybody here been there? Next time you're down there, west of Socorro, I think you can take a tour. From space, it looks like people growing mushrooms. There's a whole bunch of radio antennae out in the desert, and they can be moved around, and they all point at the same place. And remember, we talked about interferometry. That is, they can synthesize the performance of a gigantic telescope by using a number of small ones with spaces between them. And I had not seen this before, but here's VLBA, the Very Large Baseline Array, which is in New Mexico. And they see this two supermassive black holes 750 million light years from Earth, and they see these in the radio spectrum. There they are. they're in a galaxy which has, notice, no other radio sources around except this right here. So I put this in here because this is news to me. 3 years ago, people had seen once again, a binary pair of stars. You would call a black hole a star. So these are black holes that are in the neighborhood of one another, and they're orbiting around the common center of mass. And they're two black holes there doing that. And what we're seeing is radio emission from the accretion disk. These are black holes that are not super active. In fact, I think in the text here, which I'll let you read at your leisure, that these are kind of quiescent black holes. There's not much left to eat in the neighborhood. So the accretion disks are not super hot, which means they're producing radio waves, not X-rays.
We know their solar mass.
Now, this is 2.5 years old. I think if you go to this press release, you get the name of the object, and then look at it in Google, you'll see more recent results. I did not do that. So, this is interesting. Just came out in January. This is GGC 2885. This is an enormously huge galaxy that they spent some time looking at. Let's see, there's some details here. Yeah, it's 2.5 times wider than the Milky Way. Milky Way is about 200,000 light years across. This is more like 1 million light years across, and 10 times as many stars. So we're talking about, Milky Way is generally assumed to have 100 billion stars in it. This is 1 trillion stars in one galaxy. And I'll just remind you, I hope you can see, this object here, looks like it has spokes coming out. That's not at the distance of this galaxy. This object here and this object here they're closer, they're brighter, and when they develop this picture for use as a computer for consumption by the public, inevitably you end up seeing the diffraction spikes from the design of the Hubble telescope. Remember, we talked about this, that the modern telescopes, there's a mirror looking at the sky, and in the center there's another mirror that is the secondary mirror of the telescope, and this has to be supported somehow. So it has these struts. And these struts confuse the signal processing and produce those spikes. They're probably hard to see unless you walk right up to, actually, let's do this.
We can see it.
Oh, okay, you can see it, yeah. So these spikes are always a challenge. Now, what amateur astronomers have pushed this science ahead by doing this. They make the support for the secondary mirror in their amateur telescopes curved, and then you don't see a straight line in the imagery. It's sort of, this produces kind of a fuzzy background, but it doesn't affect the quality. The amateur astronomers have, as you will see in a minute, are continually doing great things.
So the dots in front of the galaxy are basically stars in the way up.
Yeah, right. And this guy has, you can see it's a spiral, it has arms, it's tilted, so we're not seeing it face on, we're seeing it tilted, and it has a companion over here. Just like we here in the Milky Way, we have two companions. We have the large and small Magellanic Clouds, so named by Magellan. And they are in orbit, the Magellanic Clouds are in orbit around the Milky Way, and this, I don't know if this has a name, but In any case, the Godzilla galaxy is out there, and it seems like it's dormant. That is, it's not super active in producing new stars, and it looks like it's been quiet. By looking at the chemistry of this galaxy, which is done by doing spectroscopy, we can see the density of different kinds of elements. It hasn't been super active in producing new stars. And one theory is that it's big because it ate the neighborhood, and it's quiescent because it ate the neighborhood. There's nothing more to eat, and there's nothing else nearby to tangle with it. So, oh, yes, and James Webb. So let me remind you, this article brings up again something we've talked about before. The James Webb Space Telescope, which we hope will launch in 2022, works in the infrared, which allows it to see through the dust deep inside the galaxy. So we'll all be around, I'm confident, in, say, 2025 when we first start getting images from James Webb, and we will see a picture of the nucleus of this galaxy, where you'll actually be able to see the structure right down close to the active area in the center, which in this case is pretty inactive. Not a lot of new stars being produced in this object. Antimatter. So this just once again a week ago. This is amazing. So we can talk about antimatter. There is a standard model of subatomic physics, which says that every type of particle, like an electron or proton, has a corresponding antiparticle, an anti-electron, which is called a positron, an anti-neutron, which is called an anti-neutron. And you could, in theory, if you bring and this is done regularly, you make positrons in a radioactive process, and you bring them in vicinity of an electron, and one is the mirror image of the other, and when they meet, they annihilate into a puff of energy. You get a little, depending on the size of the object, you get a little puff of X-ray or ultraviolet light. So it's always been an interesting thing to think about, could we build anti-atoms? And anti-atoms have been built. This recent development involves doing something with anti-atoms, which you'll see come up on the page. So the idea is that we can build anti-hydrogen. So we have an anti-proton, which is the nucleus of hydrogen, and an anti-electron orbiting or in the vicinity of the, or what did I say? Anti-electron is a positron. Right. So you put these antiparticles together and you make anti-hydrogen. And if you're clever, you don't let it come in contact with any hydrogen in the neighborhood, otherwise they annihilate. And you can study anti-hydrogen. Now, to understand the study they did, we have to talk about something. Let me pull this up. We have to talk about the Lamb effect. This is a discovery in the late 1940s, and it goes this way. If you take hydrogen, it's got an electron. The electron is interacting with two things. It's interacting with the proton, so it's a hydrogen atom, it has a proton and an electron. The electron's interacting with the proton, that's how they form an atom, but the electron is also exposed to vacuum. Around this atom, there's nothing. And this empty space has energy in it, created by quantum fluctuations, this unpredictability effect from quantum mechanics. So the electron is interacting with the proton very strongly, and in a very subtle way with empty space. And Willard Lamb, I think is his name, managed in the late 40s and early 50s to measure the properties of that electron in hydrogen and compare it to a bare electron. And you can see a little difference in the energy level because the fact that these electrons are interacting with the vacuum. You'd think normally a vacuum is empty, there's nothing in it. But there is fluctuating energy there. And Lamb, who won the Nobel Prize for his work, he and another guy, they measured something called the Lamb shift. That is, if you measure the energy levels of that hydrogen, that energy level is not where you'd expect it because the electron is interacting with the vacuum as well as the proton. So these geniuses who published this paper of last week said, we're going to do the same experiment with anti-hydrogen. Already this is crazy time because it's difficult to produce anti-hydrogen, but they measured the Lamb shift in anti-hydrogen, and they get the same result. That is, the model that we have for subatomic particles seems to hold up even for antiparticles, and that's, one way it's good, it means the theory's right. The other way it's really bad because we didn't discover anything. The theory is, we never want to get to a place where we can explain everything.
Well,
It would be just terrible. Yes?
I have a question. I thought that a vacuum in space is a misnomer, that electromagnetic rays of any kind are ubiquitous.
Yes.
So you can't get outside that atom into quote a vacuum.
Right.
Do you understand my question?
Yes, but the vacuum that you're describing, this, if you take a volume of space and empty it of all atoms,
Yeah.
there's surging activity in there. As you say, there's electromagnetic radiation,
Yeah.
there's particles, some of them are massive, but they only last a short time. There's an uncountable number of tiny particles. Everything is in a box of empty. It's full of stuff. But it's different than how things would be if it was truly empty. That is, this electron interaction with the vacuum. Vacuum, it turns out, is a bad word. I mean, we all think of, we have a vacuum at home and it sweeps up the dust, but there's no such thing as a true vacuum. It's filled with subatomic particles surging in and out of existence all the time. Question, yes, sir?
Do we know why we have matter and not antimatter in our universe?
No, we don't. And next week, I'm going to talk about that. This is a mystery. The early universe, I mean, if you started from scratch and say, well, we know a lot, let's write it all down. First thing we say is when the universe was created, an equal amount of antimatter and matter should have been produced. So where's the antimatter? We never find antimatter. Like if you look at the stars and galaxies and stuff, never find antimatter stuff.
How do you know?
Well, there's ways to know. It has to do with interactions of matter with magnetic fields and electric fields. You could tell.
Okay.
But we never see anti-stars. We never see anti-galaxies. Nobody knows why there's this imbalance. It's an unresolved mystery. So the good news is we understand enough about anti-hydrogen to know that our model for subatomic physics is correct. Notice the last line. It says 10 years ago, anti-hydrogen was, nobody had ever produced anti-hydrogen.
And it
Yeah.
can't be the dark energy that we don't know anything about?
Yeah, well, so I'm glad you said that. I'm going to show this next week. Here's a totally mysterious thing. If you take a box of empty, it's surging with stuff. And in the late 40s, theory evolved about how much energy is in an empty box. And it's a calculation my high school students do. And you get a number. And you could say, we now know there's an empty space has energy in it, and now let's compare that to the energy in empty space that is propelling the accelerating expansion of the universe. They should be the same number, because if you've got an empty box in the laboratory, and we know how much energy is in there, then take that box out into the universe, what's the difference? It's an empty volume of space. And the two numbers, the one for the expansion of the universe, the vacuum energy of expansion, and the vacuum energy that is predicted and measured in the laboratory